Now let's talk about the relationship between pointers and arrays. Now, arrays and pointers are closely related in C and can sometimes be used interchangeably. You can think of the array name that you give an array when you declare it as a constant pointer, meaning a pointer that cannot be directed or pointed at another location. We can use pointers in a similar way as array names. So let's look at an example. Let's say we define an array called B containing 5 elements, and let's make that an integer array, and let's also define an integer pointer, and let's call it B pointer because it's a pointer pointing at array B. So B pointer will be initialized to the address of array B, and that can be accomplished as simple as this. And if this looks a little too simple to you, you can think, or you can also do it or think of what's happening as this statement. B pointer is being initialized to the address of the 0th element of B. Now, elements, or let's pick a specific element. Let's pick element number 3 of array B. Can, of course, be referenced using the index notation that we're already familiar with. But an alternative way to reference that same element is this, using pointer arithmetic. Now, we're already familiar with pointer arithmetic. Now, to access element number 3, we're adding 3 to B pointer, and then we're converting the whole thing. We are applying the dereferencing or pointer operator to the whole thing to access the actual element in that location. Because remember, B pointer is just an address, is just an address. Adding 3 to it will still give us only the address of the 3rd element of the array. To access the element, we have to use the array operator. Also the pointer operator. 3 in this case is the offset to the pointer in terms of number of elements of the array. The offset is then simply just an indication as to which element of the array should be accessed or is being referenced. So it is performing the same job as the index number in the index notation of accessing arrays. This notation is called pointer offset notation. And like I said, the parentheses are necessary because if we don't apply the parentheses, the pointer operator will be evaluated first, and that's not what we want to do. So in other words, if we don't use the parentheses, if we do something like this, this will access the 0th element in array B and add 3 and add 3 to that and show us that. So basically, in other terms, that would be the same as this. That's not what we're looking for. What we're trying to do here is we want this to be the same as this. All right, so that's why these parentheses over here are necessary. And just like that, now that you understand how what this notation here means, if what you're really interested in is just really the address of an array element, so something we would in index notation represent like this, getting the same thing using pointer notation, meaning b pointer, would be represented like so: b pointer plus 3. We are skipping the dereferencing or pointer operator, the asterisk. So whether you use this notation or this notation, both can be used to access the same element number 3 in array B. In general, all indexed arrays can be written using this pointer offset notation. Now, because we initialized b pointer to the first element in array B, B still points to the first element in the array. It doesn't change the name of the existing array. But there are also alternative other notations. So pointers themselves can be used in a more friendly looking indexed way. So for example, to access the first element, or element number 1 I should say, of array B, I could use the pointer in this form, in this notation, and that would be the same as B1 using array indexing notation. So this and this are equivalent. So this is yet another notation. This is called pointer index notation. This one over here. Pointer, because we're using the pointer to reference the array, and index because we're using a number in these square brackets. Now remember that there is a difference though, that pointers may be non-constant, which means you can change the addresses that they're pointing at, that they store. But an array name is a constant pointer. That means that you cannot do things like this, for example. You cannot change the location that the array name points at. An array name will always point at the 0th element in it. So this would definitely give you some kind of error. This is invalid. So like I said, try to modify the value of an array name with pointer arithmetic and you'll get a compiler error. So then there are 4 different methods for accessing, for referencing elements of an array. The first one is array indexing, which is simply using an array, which we've now done for a couple of times. And there's pointer offset notation with the array name as a pointer. Then there's pointer indexing notation and pointer offset with a pointer. And we can use any of these 4 notations to go to access elements of an array, in this case array B. So let's take a look at an example. So let's stick with the same names. So we have an array this time of size 4, an integer array called B containing elements 10, 20, 30, 40 that we're initializing it with. And we also have an integer pointer called b pointer, which we initialize to the start of array b, 0th element of array b. So what we'll do in this program is we'll try out all 4 notations to access all 4 elements in this array b. So first, let's use simple array index notation. This is the simplest one, the one you're already familiar with. And we have over here, actually for all 4 of these notations, we'll have a for loop over here that runs from I0 to the size of the array. And we print out the notation that we're using. So in this case, b of whatever the index number is equal to, and then we access the element, in this case, bi. So that'll be b0, b1, b2, and then b3. Next, we try accessing all 4 elements, this time using the pointer offset notation. And everything over here, the loop, structure, etc. is the same. But look how we're accessing the 4 elements over here. So this is b is the name of the array, being used kind of like a pointer. And we're adding to it an offset number, which is the loop counter. And then we're using the pointer operator over here. And you'll see this will produce the same result. But we're using a very different notation to access each element of the array. Next, we use pointer index notation. And again, a for loop going from 0 to less than 4. And this is the notation we're using over here to access all 4 elements of the array. So you can see we're using the pointer with an index. And finally, the 4th option. This is again where we use this offset notation, but over here we are using the pointer name, b pointer, plus the offset, and then putting a parenthesis around that and applying the pointer operator again, dereferencing that address. And when we run this, you'll see an output like this. As you can see, whether you use the array index notation, pointer index notation, array offset notation, or pointer offset notation, in all 4 cases, you're able to access the 4 elements stored in that array. You have to get used to the idea that there are many times there'll be different ways to accomplish the same task in programming languages. Okay. So let's look at another example now that demonstrates the relationship between pointers and arrays. So this too will demonstrate the interchangeability of arrays and pointers. And we'll look here at 2 string copying functions. One is called copy1, the other one is called copy2. What both functions do is they both copy a string into a character array. Now, based on just the function prototypes, the arguments and the return types of these 2 functions, copy1 and copy2, it seems like both functions are identical. They accomplish the same task, they take same arguments, but the difference is on the inside. They're implemented differently. So, okay, so let's have a look. One thing I want to point out, there was a slight error, I think, in the slides, in the code. So there's a const keyword that was missing in front of string 2 over here. If you don't put the const keyword over here, this line, the statement, will actually give you an error. You won't be able to compile this without it. Okay. All right, so what do we have? We have a symbolic constant size set equal to 10, and we have the prototypes for functions copy1 and copy2. In the main function, we define a character array called string1 of length of size 10 characters. And we have a constant character array called, we have a constant, we have a character pointer this is a pointer to a character constant, and it's a constant string hello. So instead of creating an array with a name and then creating a pointer to point at that array, we're skipping the first step over here. We're skipping the step of creating the array and giving it a name and then having a pointer that then is used to reference the array that already has a name. So we are creating a constant string and then setting up a character pointer to point at that constant string. Okay, we then call this function copy1 that we'll look at in a minute. And after copy1 is called and executes, we print out string 1. Then we create another character array called string 3, also of size 10, and a character array called string 4 with this inside it, goodbye. And we demonstrate the use of the other function, copy2, by using string 3 and string 4. When we finish, we print out string 3 again. So copy1 will copy string 2 into string 1. When we call the copy2 function, that will copy string 4 into the uninitialized string 3. Okay, let's take a look at the two functions. So we have copy1, and we have a for loop over here. That's interesting. So we have counter variable I initialized to 0. And interesting thing with both functions is that they both have for loops, but they have no statements inside the loop. Everything, all the copying is happening in the body of the for loop. And I'll explain that in the following slides. Okay, so what's happening here is we are receiving constant pointers to characters and for S1, and a constant pointer to a constant character array as the second argument in function copy1. This means the elements of S2 cannot be changed, should not be changed, correct? Now, what we're doing over here is each character from S2, in each iteration of the loop, character from S2 is copied into the corresponding location of S1. Now, one thing, whenever you perform an assignment operation, the output of that assignment operation is whatever character is copied over into S1 in this case on the left side. Now, how long do we want to keep copying characters over here? Well, until we hit the null character. So we do that until this is as long as S1 is not assigned a null character. When it is assigned a null character, that will be the condition to exit the for loop. That's what's happening here. So the loop condition is interesting. And we have a similar condition in copy 2. So in copy 2, we receive as the first argument a character pointer. And in the second argument, we receive a pointer to a constant character. Again, this is appropriate because S2 should not change, or the character pointed at by S2 should not change. But the pointer S2 itself, the address stored in S2, that is allowed to change. It's because we have this second const keyword is absent over here. Which means when we loop through elements of S2 or through characters pointed at by S2, we are allowed to increment or decrement, modify the value of the address stored in S2, and that's what we do over here. So see, the for loop works differently. First of all, there's no need to initialize anything, which is why over here there's no statement in the first part, no initialization happening. Pointers to characters are incremented directly in the update part of the for loop, and in here, kind of the same idea. We copy one character from pointed at by pointer S2 into the location pointed at by S1 for as long as that character is not the null character. When it is the null character, that is our condition to exit the for loop. Now the following slides explain all of this in great detail in text form. I thought it would be more appropriate to explain the things that are happening here directly in the code while you have the code in front of you. So like I mentioned, copy 1 uses the array index notation to copy string S2 into S1, into array S1. The function defines counter variable I as array index. The for statement does all the copying. The body of it is empty, like you saw. The copying process itself happens by this assignment operation, and when the null character is encountered in S2, it's assigned to S1, of course, but the value of the assignment becomes the value assigned to the, of course, to the left operand. And when that happens, the loop terminates when the null character is assigned to S1. Function copy2 uses pointers and pointer arithmetic to copy the string in S2 into array S1. Again, the for loop statement header performs all the copy operation. There's nothing inside the for loop, the body of the for loop. And over here, the header does not include, so no initialization, and this expression over here is very similar to what we saw in the function copy1. However, we're using pointers, pointers that are updated, that are changed in each iteration of the for loop. Pointer S2 is dereferenced, and the character it is pointing at is assigned to the dereferenced pointer of S1. And after each such assignment, both pointers are incremented. The stop condition, the exit condition is the same. When the null character is encountered in S2, it's assigned to the dereference pointer S1, and that gets us out of the for loop. Now the first argument in both copy1 and copy2 must be an array, and it must be large enough to hold the string in the second argument. It must be large enough to fit in all the characters from the second string up to the null character. If the null character comes much later and we overrun the array, the size of the array S1, we can expect to see some kind of error. The second argument, which contains the data, the string that is to be copied into the first argument, in both cases is declared a pointer to a constant character string. And like I said, the arguments are similar in the sense that the second argument is what's copied into the array, which is the first argument. Characters in both cases are read one at a time, and no changes are made to the source data. And that is why the second parameter is set to point to a constant value, following the principle of least privilege. After all, we're only copying, so there's really no need for any function to make any modifications to the second argument. And that gets us to the start of a related topic, that is arrays of pointers. Now, arrays themselves may also be made up, maybe arrays of pointers. We haven't used that up to this point. And a common use of that is to make an array of strings. And another name for that is a string array. I'll show you how you can imagine that graphically. Now each entry in that array is the starting address of a string. And we already know in C, a string is just an array of characters. So in this array of strings, each element is a pointer to the starting address, to the first character of a string. pointer to the first character of a string. And let me show you how we can set that up. So let's define an array of pointers in which each element is a pointer to a string. And that can look as simple as this example over here. So we have over here an array called suit of size 4. It is of type character arrays, character pointers, and also declared the strings themselves are constant, meaning they cannot be changed. Not only that, we are, and because they are constant, we are also initializing them over here. We're initializing the entire array, suit. And the first element is the string hearts, the second one a string diamonds, third one clubs, fourth one spades. So this means size of the array is 4. Like I said, this means it's an array of type pointer to character, and const specifies that the strings that we're pointing at will not be modified. And then there are, of course, the 4 values, the 4 strings that the array, the pointer array of pointers points at. Now each of these 4 strings is of course terminated by a null character, which means this one looks, the first one looks to have 1, 2, 3, 4, 5, 6 characters, meaning it's actually 7 characters long because there's a hidden null character. The same idea applies to all of the others. So in this case, the length of each of these strings is 7, 9, 6, and 7 in this example. Now they're all different. You can see that. Not all different. 2 of them are 7 characters long. So this array that we're making up, this is only storing the pointers, the 4 addresses. That's it. Each pointing to the first character of each of those strings. Now the array called suit that we just defined, that is fixed in size. But it can access character strings that can be of any length, different lengths even, as we see up here. And this is a nice flexibility that we have in C. So in this particular example, this is what this array of pointers would look like. So this is our array, size 4, suit, and each element is a pointer pointing to a string somewhere else in memory. Where? That is what each of these array elements contains, that address. Now, it's also possible to simply create a 2-dimensional array and store all those strings in that. Of course, you could do that, but that would also mean that you're wasting memory. And how much? Well, you see, the number of rows of the 2-dimensional arrays would have to be 4, because we have 4 strings over here. But the number of columns would have to be equal to the length of the longest of these strings, meaning 9, which means one, 2, 3, 4, 5, 6, and 7 characters would be going to waste. Now imagine if this particular string over here, or any one of these strings, was really, really long, and the other ones are maybe not that long. You can see how that wastage of space in a two-dimensional array could become huge. And that is what, if it suits your situation, that is what using an array of pointers can help you avoid. You'll only be using as much memory as you really need.